This is the third in a series of presentations on system requirements analysis, papers that I've done for the International Council on Systems Engineering. I'm re-recording them because we don't have videos from 1998 on these, but this was presented to the symposium in 1998 at Vancouver, British Columbia. And this paper ties together the prior two papers, SRA1 and SRA2, on anomaly handling and failure identification as means to achieve requirements completeness. And the intent of this paper was to tie those things together. At the time, I worked for the Boeing company, and that's not specific to the content of this paper. It's just information. So what I want to talk about is to be able to present to you so that you will be able to achieve completeness of requirements in a set of requirements that you're considering. So 3 steps necessary and sufficient for producing complete requirements, how we can test for that or measure that. I want to emphasize that requirements completeness is not absolute, but it's relative. And I did a paper in 2001, and it's in the Systems Engineering Journal as a correspondence about that. We'll talk about that specifically in this presentation. And understand the critical role of stakeholders in problem definition as related to whether there is such a thing as absolute completeness, or whether it really is a situation of relative completeness. And this particular paper formed the basis for the INCOSE Requirements Working Group project on the same subject. And there will be another presentation on that paper from 2004. But this is the first version that was prepared. So when we talk about what the objectives are, the motivation, and then the analysis model, sensitivity, and conclusions. So some definitions. I used the word deterministic in the title. What I was interested in is not a way we can achieve completeness by review, but a methodology so that we would know when we were finished that we had a complete set of requirements based on some specific criteria and methodology. So we want an inevitable result. That's what I mean by deterministic. The mission or problem statement or need, these terms are used somewhat interchangeably to mean that the problem which is to be solved by a process which includes requirements definition. Typically, that set of requirements is the output of that prior analysis. A stakeholder, and this is the definition from the EIA 632 standard, an enterprise, organization, or individual having an interest in or a stake in the outcome of the engineering of a system. And it's important to realize that these aren't just customers, not just acquirers, not just users or maintainers, but it's literally anyone who is going to be affected by and therefore has a stake in the system. Someone said in the INCOSE context many years ago, even if they're not explicitly represented, if they're affected, they will make themselves known eventually. And you can think about public intervention in system development as an example of that. Requirements are statements about a system that define the who, the what, the how well, and under what conditions, the function and performance characteristics that the system is to be created to for definition, testing, operation, maintenance, disposal. These are mandatory characteristics. I make more about of that subject in the 2004 presentation. So these aren't simply desires, but these are the mandatory characteristics, how we will determine acceptability or not of the system. There may be additional requirements about how the system is to be made, the physical characteristics or other suitability criteria. But each of these has to be defined by the who, shall, what, how, well, under what conditions. And then the last one is define attributes of the system which are, I would, instead of saying significant, are required by the stakeholder as a condition of acceptance. So I would update the language here, given when I'm doing this now compared to when I first wrote it. The motivation. Well, requirements drive the system development, or at least they should, and therefore they cost money to define the requirements, to argue over the requirements, to implement the requirements, to maintain the requirements, to verify the requirements, to change the requirements, for all sorts of reasons. So they're expensive. And if you have too many requirements, then you're wasting money because you're defining things that don't need to be defined. And you're also over constraining the design, meaning you're narrowing the potential solution space without a valid reason. So too many requirements aren't a good thing. Insufficient requirements also waste money because you have inadequate specification and design that will probably be covered in discovered in test and integration, or maybe during operations, because you realize, or the user or the sponsor realizes that, oh, we forgot something. So we really want to know that we haven't missed anything. So it's important to know that we have not too many and not the situation of not enough, but just right. We also want to be sure that all the requirements we have are correct, because incorrect requirements waste money. They drive the design, but it may end up being an incorrect design, and then the design and the test have to be redone. So this work was stimulated by a question that was posed to the INCOSE Requirements Working Group, which I joined, I think, in 96 or 97. How does one determine when requirements are complete? And this was recognized as an issue. The methodologies that were proposed at that time, Jeff Grady in his book on system requirements analysis, focusing on reviewing the requirements for completeness, comparing it to a template, for example. I was not satisfied with that. I thought there might be a better way to do it. A seminal paper by Pradeep Kaur and Bailey identified the difficult problem of identifying requirements which are necessary but are missing. The missing requirements is always a more difficult problem. If you have a requirement, you can analyze it to see if it's correct. But if you're missing a requirement, you don't even necessarily think about whether you're missing a requirement. Brian Marr, who was the Boeing Professor of Systems Engineering at University of Washington, INCOSE Fellow, and founder of INCOSE, had several thoughts that, well, you need to make sure you address all categories, scenarios, and states, but didn't really go much beyond that. So I was not satisfied with the level of definition of what it means to get to completeness of requirements. So if you go and listen to the prior two papers on anomaly handling and failure identification, the idea of completeness of requirements comes through very strongly in both of those papers. And this is, as I said, this paper is intended to tie those together and make it clear how you achieve completeness of requirements. So it's a three-step process to get complete requirements. Define the problem. This is absolutely key. From that problem definition, develop complete requirements, and then verify that the requirements are complete. And there may be some interaction and iteration, but the idea is we need to know what the problem definition is. What problem are we trying to solve? Are there any constraints on this issue? And then defining the problem is based on Well, who's defining the problem? What do they care about? What are their measures of success? What is the current issue that is a problem? And as in any problem statement, there may be some that are better than others with respect to the stakeholders who are defining it, but there's no absolutely correct statement of a problem. A problem statement is a problem statement. So part of getting to completeness is who's participating in the problem definition. So it turns out this is the most important and the hardest step, is this first one of problem definition. Once we have that and we can quantify that, then it's easier to derive the requirements from that and be sure you've covered everything. So I'll go through each of these in a little more detail. First, define the problem. So first thing to recognize, and this was made explicit in the 1996 paper, the SRA3, that if we're not going to over-constrain the design, then all the functional requirements have to be manifested at the boundary of the system we're analyzing. Because if it's not observable as a behavior and measurable as a behavior at the boundary of the system of interest, then it's probably not a valid requirement, at least not a valid functional performance requirement at that architecture level. Well, that means that the requirements analysis related to mission and function reduces to interface analysis. What is happening at the interfaces? So if we define the various missions and the life cycle phases or operational phases, understand all the inputs and the outputs, clearly identify those interfaces, and then quantify them, because that's what we're interested in. Given a set of inputs or a test vector, what are the measurable outputs and what are the required values that they have to have? Now, it should be evident that interfaces depend on the context. So I will come up with different output requirements based on the associated or contextual systems with which we're interacting, whether we're receiving specific inputs or generating certain outputs. What those are depend on what is in the context. So it is affected not only by external systems, but also stakeholders. Stakeholders who have a stake in the characteristics of the system, the behavior, and their associated requirements. We use context diagrams, and these are critically important in systems engineering to clarify who or what is interacting with the system. You will come up with a different problem statement if you have a different set of stakeholders or a different set of associated systems in the context. You may also have different interfaces for different program phases or operating modes or lifecycle phases. For example, the test interfaces may be unique for testing activity and not required for operations, but that you still need to have them, but their characteristic behaviors will be derived from a test analysis. So the quantified interfaces define the under what conditions and the measurable how well of each function or each what. What is the input? That's part of the condition or the state of the system. What's the output that we can observe, and what's the measurement of that output that allows us to determine how well? So that's what I mean by quantification. Requirements elicitation processes can help define the problem using such techniques as quality function deployment, QFD, prototyping, mission analysis, measures of effectiveness analysis, objective function analysis. Sometimes these will be in conflict. And someone, the requirements analyst, is going to have to reconcile and prioritize those things, because it may be, for example, that stakeholders, not all stakeholders can be maximally satisfied at the same time. Obvious example, performance versus cost. We want to maximize performance, but we want to minimize cost. Well, there may have to be some give up. You have to give up some performance in order to get a price that's acceptable to the acquirer or the user. What is important to realize is that the degree to which critical stakeholders are missing or their requirements are unquantified generates a degree of external risk in the system development. Even if we do everything exactly right in the system development, if we're missing a stakeholder and something they care about, and we find out about it at the end, we just created a very large programmatic feedback loop to fix the system because we forgot about a measure of effectiveness, a certain function, an associated system, because we forgot about a stakeholder. So this identification of stakeholders and the things they care about and associated systems and their interfaces is what's critical about getting to completeness of requirements. So here's a simple example about the interface problem. If I have a functional requirement to provide power, and even if it's quantified, provide 35 watts of power, I will end up with two very different design concepts depending on how the interface is characterized. For example, if it's a DC power supply, then I might describe the power as being conducted at a certain voltage. On the other hand, if I want to provide radiated power for something like a heater, then I would describe the interface not as conducted, but as radiated. And I might have to specify a wavelength or a temperature and what the target radiation is, so I know how much heat transfer I'm going to get based on the temperature difference. So the point of this is, even if I say I have a requirement to provide power at 35 watts, that requirement is incomplete because I haven't specified the interface. And we can get ourselves in trouble by making too many assumptions about, well, of course, everyone knows that's the interface. But then the designer or supplier comes back and says, well, I'm doing this, a conducted power supply, and what you really needed was a radiated heater. And they'll say, well, I met your requirement. You didn't specify the interface. So that's why I say interface characterization is absolutely essential to specifying complete requirements. And you'll see this in the ensuing papers. But again, it's the who, shall, what, how well, under what conditions. Step 2 is to develop complete requirements from the problem statement. So one of the things I tried to assert in the prior paper from 1996, it's sufficient to examine the interface's overall possible conditions, the physical range, in order to assert completeness. Because if all combinations of external interface conditions are analyzed and we have an associated behavior that's defined for them, in other words, a requirement, then the requirements are complete, because there's no condition of the universe that isn't included in that set of conditions. And as I've said in prior papers, I ran into this first with regard to software, because they do examine all possible states of inputs and combinations of inputs. And if your requirements don't address all of them, then you will have incompleteness and subject to questions from your software implementers about what you want to have happen under certain conditions. Where the stakeholders get involved is they may have not thought about a particular condition or set of conditions. So the assertion of an associated behavior may need to be validated with the stakeholders to ensure that that behavior is acceptable. I will certainly assert that as a systems engineer, I can't presume to know everything the various stakeholders might want a system to do under a set of conditions that they hadn't thought about. But it would certainly be important to at least assert a behavior rather than asking what they want done, just assert a behavior and ask them if that is acceptable. If it's something they hadn't at first identified as a specific set of conditions they wanted addressed. This typically arises in the what if conditions, not the go path, not the things that I know I want the system to do, but in the conditions that I hadn't thought about that arise from Murphy's Law. We'll talk about that later. Things go wrong, combinations of inputs that we hadn't thought about. And these may depend on certain trade-offs. Yeah, I'd like to operate through a set of failures, but we can't afford the redundancy. So we're willing to operate, for example, in a degraded capability when we have a certain set of failures. But we need to get that situation defined so that when that occurs, we have a requirement that covers that condition. I will say that it is certainly difficult to examine the interface's overall possible conditions because it can end up being an infinite set of permutations of all interfaces and all their possible physical states. Say that ends up being a very, very large number. So we'll next talk about how we get that to a manageable set, but part of this will be programmatic choice. What are the combinations that you want to clearly examine and make sure you have a defined behavior for? So if we have to examine all combinations of the interface parameters, which is what I asserted in the prior paper, then either we need explicitly defined behavior for each combination or some sort of precedence. Like in this table or this graphic here, I might say, well, I do want to examine all parameters across all their ranges, but for some combinations, for example, in this shaded area here, I may not, if P2 is not valid, then I may want to assert the behavior associated with whatever P1 is in that range. Or I might want to have, in this case, 1, 2, 3, 4, 5, 15 different behaviors. And it depends on the kind of system I have. Or wherever it says invalid, I may want to say, do a specific common thing so that all 6 of these invalids have the same behavior, in which case my list of conditions includes these explicit combinations of P1 and P2, but I have only a single result, which means that's one requirement. The key is that the union of all antecedents must constitute the universal set. That is, there can be no sets of conditions for which I cannot find the associated behavior in the requirements. That's how you get to completeness. And as I talked about in the first paper, it's the else condition that allows you to get there with confidence. That is, if I define behaviors for P1 and P2 both valid here and here, I could write a single requirement that says if either P1 or P2 is not valid, in other words, in this box or this box, then the system should do something that would cover these other 13 conditions. But I did it with one requirement. Now, exactly how you decompose that is going to be up to the analyst in consultation with the various stakeholders. Because they may say, well, that works for P2 in this range, but that's not okay for P2 in this range. Okay, so we need to create a new behavior for P2 in this range. That's determining the correct behavior in consultation with the various stakeholders. That's why this process depends on stakeholder input for conditions that they may not have thought about. I guess in one sense, this is similar to what we try and do in Agile, is get the user involved in validating that what the system is going to do is okay. Only in this case, we're getting the user involved or the stakeholder involved while we're doing the requirements, not while we're writing the code. Lastly, then, having gone through the process of producing complete requirements, we want to verify that we actually have produced a complete set of requirements. So I use the test from my first paper, 95, no requirement set with unique antecedents is complete. So requirements completeness. It's not complete unless the union of all antecedents is the universal set of all possible conditions. So this is applying set theory to the sets of antecedents to make sure they're actually complete. So do we have a defined behavior for all possible conditions? And then we need to verify or validate, if you will, the system responses that are defined in the requirements with the stakeholders. Under this, for example, under this failure condition, is this the appropriate behavior? You know, loss of power, loss of communication, and I refer you back to the 95 paper on the anomaly handling to find some of those, and the 96 paper that covers how we find all of them. But it will be up to the system requirements analyst working with the stakeholders to verify that the responses that have been proposed by the requirements analyst for those specific sets of conditions that the stakeholders hadn't thought about before are what they are willing to accept. So that's the verification of the completeness. So is there anything missing? Well, let's go through what we might have missed. So our analysis process, we still have to go through architecture development, trade studies, life cycle costs. We still do those things in response to the problem statement and the definition of the requirements. What is key is, who do we identify as the stakeholders? And from that, what interfaces and or other constraints are part of the problem definition or constraints on the solution? Once we have all the behaviors, then we can analyze and focus on the performance trades as primarily related to the correctness of the result. And that's a potential form of completeness. Do we have the correct performance value? But we don't have to wonder if we have all the interfaces and all the functions, because our analysis has allowed us to identify all the combinations of interface parameters and derive behaviors. And then it's a matter of sensitivity analysis and other trade-offs to determine whether we have the appropriate performance value. You know, is this timing too strict? Is this acceleration too large? In other words, does it drive too much risk into the program given the budget and schedule? It is important to understand that the failure to identify a stakeholder up front or any associated subsystem is a potential hole in the analysis. And that's the hardest part of this process. In the 2004 paper of the same topic, we talk about that in more detail, because this is hard. And it really is a choice. Hey, do I want to include that particular stakeholder in the problem definition or not? This is similar to performing trade studies and who gets to decide what the criteria are and their relative importance. If we leave out somebody, then their concerns may not be included. And that has pluses and minuses, but it can create a risk of having to do rework in the future. Similarly, if we miss a stakeholder or an associated subsystem or a concern of a stakeholder, then we may have rework. So the methodology for completeness is critically dependent on coming up with the set of stakeholders and their concerns. And as I said earlier, it's not absolute, it is relative. So there's no proof of unconditional completeness because problem statements change and mission statements changed and associated systems change. But this gives us a means to track the implications of change in those areas. We have a new stakeholder. What do they care about? Or we have a new set of environments. And I've worked on systems where we had that, and all of a sudden, requirements weren't going to work for a new set of environments, or there's new design constraints because certain interfaces are not okay or certain kinds of interfaces are required. So any change in the stakeholders, their concerns, or associated systems and contexts means we need to reassess completeness. Do we have all the behaviors identified for all the possible combinations of conditions we're concerned about? And are the behaviors acceptable functionally and quantitatively with respect to what the stakeholder needs, concerns, and requirements are? The importance of the problem statement cannot be overemphasized. This became very obvious in a companion activity that was published. There's the reference by Terry Bayhill and others called the Design Methods Comparison Project. And the original problem statement was to present a standard problem and describe alternative design methods. But the problem was given. But on the INCOSE discussion list, this quickly evolved into a discussion regarding the correctness of the problem statement. And Ira Glickstein made it very explicit. He said the real systems engineering does not consist of blindly following the problem statement, but of questioning it in light of stressful cases, failure modes, and perhaps other stakeholders who maybe weren't consulted in the original. So the problem to be solved depends on who the stakeholders are, and a key trait of good systems engineers is to examine the problem statement and make sure it's the correct one before we go off and attempt to solve it. So in this case, the original problem statement was the original problem statement. It was neither good nor bad. It was neither correct nor incorrect. But someone may have determined that it was incomplete because it didn't cover a situation that it was of a concern to a particular stakeholder or life cycle phase. And whatever we eventually decide as the problem statement we're going to work on is going to result in a particular set of solutions. So this eventual solution space is inextricably linked to the problem space. And that's important to know. And no solution can be evaluated apart from the problem statement and the inherent stakeholder interfaces, which is why we say requirements completeness is not absolute, but it is relative, and it's relative with respect to who's defining the problem and what do they care about, and how does a system of interest need to interact with its context and environment. So The summary here is requirements completeness can be defined in the context of a problem statement. It's not absolute. It depends on who's involved in the problem definition. So if we want stable requirements, then we have to have stability in the stakeholders, their concerns, their measures of success, and the associated contextual systems and their interfaces. If any of those things change during the development, then that will affect the requirements, and therefore that will affect the design. Once we believe we have accomplished completeness of requirements, we can measure that and test for it by the set analysis of being able to ensure or evaluate that all possible combinations of interface conditions are truly addressed in the requirements with one or more defined behaviors. And again, requirements completeness is subject to the vagaries of any development process. Things change. The problem may change because of the contextual situation or the environments or the world situation. Stakeholders may change. And anytime any of those things changes, the problem may change, and therefore the requirements are going to change. And it's important that we understand how every requirement is related to something else, a concern, a particular stakeholder need, a measure of effectiveness, a risk, a contextual system, a life cycle phase, whatever it is. We cannot simply be asserting requirements without some rationale. So thank you for your attention, and I look forward to seeing you on the next presentation.